So rather than actually breaking this lecture down into a specific set of subjects, what I'd like you to do is, as we go through the different parts of the lecture, think about some points to consider in terms of the development of nuclear power since its creation in the early 1950s, to where we are at the moment. So for example, what's driven us from the first reactor, Chicago Pile number 1, to our generation 3+ civil nuclear reactors in about 75 years? What are the driving forces? Political, technical, or what different driving forces have existed between civilian and military development? For a long time, certainly in the early stages of the nuclear industry, the two were indistinguishable. So which dominated in the past and what do we think dominates now? How have those driving forces changed for civilian development? The original reactors were built under very different conditions than reactors are being built under today. And how important do we think external events are in terms of shaping the strategy, certainly in the UK, for nuclear build and nuclear operations? So let's start the first part of this lecture, and the lecture is broken up into 4 different parts that span the chronology and the history of nuclear power, specifically the creation of it in the early 50s through to where we are now. And this first part's entitled The Birth of Nuclear Power. So let's turn the clock back, all the way back to 100 plus years ago, when we first discovered radiation existed. And in fact, that was really the start of electricity generation in terms of it being used as a power source for all sorts of things. So if we wanted to generate electricity 100 plus years ago, and there wasn't a huge demand for it by then, obviously there was lots of steam and horsepower and things like that. 100 years ago, gas existed, but it was pretty much used exclusively for cooking, and it wasn't natural gas. It was what was called town gas that came from coal. There was certainly wind power around. You'll see lots of historical buildings called windmills that directly drove grinding stones for flour, so certainly nothing connected to power or electricity generation then. Solar, well, solar was pretty much the sun being used for relaxation. It was coal. Coal was king. Coal was what was being used to burn and create steam, and that was the only power source that was being used. So we learned in the introduction slides and also the second lecture series about the discovery of X-rays and radioactivity by Henri Becquerel, and very shortly afterwards Ernest Rutherford discovered alpha and beta rays. So we've got the formation of radioactivity, and that leads us through to 10 years of development work where we find out all about alpha rays, we find out all about natural radioactivity, and Albert Einstein formulates his E=mc² formula. It tells us the basis of how we get nuclear energy. And then we see another 10 years of development, and we end up with, by the end of 20-25 years of rapid development, we know about the nucleus and about how the nucleus behaves and how it breaks down. Now, in fact, those discoveries do have an impact on society, and the newfangled radioactivity is suddenly seen as a wonderful new thing that can do all sorts of curative and medical things that weren't previously available before. So, for example, you could buy what's called a Revigator, and the Revigator would provide you with sparkling water in the morning, and the sparkle, the fizz, came from radon gas. So you could have your own glass of radioactive water in the morning as a pick-me-up, sold by the Radioactive Water Company of San Francisco in 1905, and it came from uranium ore that had a lot of radium in it, and one of the daughter products of radium is radon. So you would fill that up with water overnight, open up your tap, and sparkling water would come out laced with radon. Or perhaps you would restore your vigour with a suppository made from radium. Fantastic for a pick-me-up and a pep-me-up in the morning, and get all those natural functions working well. Or perhaps have a nice spa weekend at the Radium Spa Palace in the Czech Republic. A number of these hotels opened up that had radioactive water that you could go and bathe in, and in fact the Spa Radium Palace is still open for business today. So the next 2 decades see a rapid development of our knowledge about radioactivity. We get the development of quantum mechanics that gives us the idea of how these forces work later on. And we see development of laboratory equipment that helps us probe and discover different elements like the cyclotron and the linear accelerator. And if you remember, these were very much part of the discovery of the actinides in Berkeley in the 1950s. Americium, technetium, neptunium and curium were all discovered using linear accelerators and cyclotrons. And we can see that the discovery of new isotopes like deuterium, and I suppose the final part of the knowledge of the nucleus comes in 1932 with the discovery of a neutron, another particle that forms very much an important part in fission. And in the space of 8 years, less than 8 years, through theory and some experimentation on uranium in fission, we get from the knowledge of that neutron all the way through to the creation or the theorization of a weapon of nuclear fission bomb. And that's when our story really begins, because the time is the 1940s and the world is at war with itself in World War II, and the military takes hold of this concept and creates the Manhattan Project. And part of the Manhattan Project is to work out how to create the material for one of these theorized bombs, a fission bomb. And to do that, you need a fission reactor. You need to take it out of the laboratory and turn it into some form of large-scale production device. And the first ever fission reactor is created and built, Chicago Pile No. 1. And that's built at a place called Oak Ridge National Laboratory in Tennessee in the US. And in 1942 it goes critical, and therefore we have our first ever chain reaction sustained in a reactor. And it's this man that spearheads it, Enrico Fermi, the mastermind and leader in terms of the technological content of the Manhattan Project. Now, Chicago Pile No. 1 is pretty primitive by today's standards and doesn't really look like a reactor in the way that it was built, but it just contains some of the key elements that we expect of a reactor even today. So it wasn't intended for power, so there's no cooling. There was no water cooling or gas cooling in it, so things got hot, but they cooled by natural convection. There was very little shielding. You can see here's the graphite core, and there's a person we were standing next to it as a demonstration, but in fact here's the mock-up of the reactor, and there was a series of graphite bricks that used the moderator. So that's another key feature of reactors today, they have a moderator. Here's a charging machine where fuel will be put into that, and people would work at this face here. So the key thing is there's no concrete or steel vessel to contain that. And one of the reasons was it wasn't intended for long periods of operation. It was intended to do a series of campaigns with fuel rods, and once they were done it was finished. So it didn't work for very long before it was shut down, because it had achieved its purpose to create the raw material for a weapon. So we've now started on the road of development from our first ever reactor, Chicago Pile No. 1, all the way through to the current generation of nuclear reactors. And in about 75 years we get from that relatively rudimentary and primitive fission reactor all the way through to something like Hinkley Point C, which is the latest reactor to be built in the world. And you can see the driving forces are extremely different. On the civilian side, we've got an age of discovery, where we're learning about the structure of the atom, we're learning about quantum physics, which develops the mathematics to allow us to understand some of the fundamental forces that hold the atom together and govern the way it behaves. And we're discovering things like Einstein's theory of relativity that gives us an insight into how binding energy and nuclear energy works to allow us to develop things like nuclear energy later on. And the dominating force is military. Hardly surprising, the world is at war, the military is wanting to develop weapons to help win that war, and that completely dominates this particular era. As we see later on, that rapidly changes and we see different types of forces, different types of strategies dominating. To recap, we can think about which groups had a particular stake in the development of nuclear power or nuclear energy. The military, well, obviously it was people who wanted to develop that weapon, the Manhattan Project, and the UK was fully integrated into the Manhattan Project, and the birth of our nuclear industry comes from that as well. Why? There was a major war on. It was probably one of the biggest wars the world's ever seen, and the military, the US military specifically, wanted to develop weapons to win that war, and that was quite time bound because it was really the 1940s, after that first 20 or 30 years of fundamental discovery of radioactivity. On the civilian side, we have famous names like Rutherford and Chadwick and Curie and Becquerel, who discovered all the basics of nuclear energy, of nuclear physics, the structure of the atom, probed into that and discovered neutrons and protons and the way in which the atom was put together. Why were they doing it? Scientific curiosity. Nobody at the time was thinking about building a power reactor. Nobody at the time was thinking about building a reactor that could generate electricity. And of course that was right at the beginning and carried on right the way through to the 1950s as well, when we saw a different type of discovery. Our next stage in the story of the development of nuclear power is the creation of the Hanford B reactor, which is the next version of a nuclear fission reactor built on knowledge gained from Chicago Pile No. 1. And Hanford is in the northwest of America and is a dedicated site that still exists. Hanford site is the place that exists at the moment and has been used for military purposes for a long time. And we can see the reactor face there is very different to what we had with Chicago Pile No. 1. First off, it's a lot bigger. It was still based on metal fuel. It was still based on a charging face where you would push fuel rods into a graphite core. In this case, there was a lot of heat produced, and so they did introduce water cooling. But all that waste heat was simply thrown away. We weren't using it to generate electricity and never intended to, so it's not aimed at power production. Interestingly enough, the Hanford B reactor was also linked to a reprocessing or separation facility where the material was extracted, because in this particular case the intention was to produce plutonium, and therefore we had to have our first real set of reprocessing or recycle facilities developed as well, and therefore there was a whole site of different facilities that were created at Hanford as part of the Manhattan Project. Well, we now have what looks like the makings of a nuclear power reactor. We've got water cooling, we've got a large core, we've got fuel charging, we've got a separate building. In fact, we've even got the beginnings of a nuclear fuel cycle where we take that fuel and we treat that in a separation plant. And in 75 years, we move from that to the current reactor that's being built in the UK called Hinkley Point C, HPC for short, which is the most expensive building on the Earth. I use the term the Earth because the most expensive building, or the most expensive thing man has ever built, is the International Space Station. But in terms of the size, the complexity, the cost, Hinkley Point C is the most expensive thing that people have tried to build and have built on the Earth to date. It is a huge undertaking. It is a massive nuclear power station. It's got two units, two actual reactor units, throwing out 3.2 gigawatts of electric. That represents 7% of the total electricity demand in the UK when it's going to be complete. It'll operate for 60 years minimum, maybe even longer than that, and it's 100% commercially funded. There's no military, there's no government funded or anything like that in there, and therefore we've moved from something that is totally military, no electricity generated, some heat, right the way through to something that is a absolutely huge power station. There's an artist's impression of Hinkley Point C. Operational in the 2030s if they keep to time. EDF Energy is the owner. There's our two reactor buildings. There's the actual reactor containment facilities there. All these are the fuel storage ponds and turbine houses. So the fuel and the turbine houses, and all this, the works outside there are non-nuclear. These are all to generate the electricity, the 3.2 gigawatt electric that's going to be powering well, all sorts of things in the future. Water cooled, so again water cooling, same as Hanford B. Doesn't use uranium metal fuel, uses enriched UO2 fuel. it's based on 2 generations of pressurized water reactor technology. So in between Hanford B and the construction of Hinkley Point C, there's been many pressurized water reactors built and designed around the world, in France, in the US, in the Far East, and all that knowledge has gone into designing these and building them. And it's been taken through a rigorous assessment in terms of its regulation. So that's the other key thing, is the Hanford B was built under military auspices, didn't have a civilian regulator, didn't have any rules associated with how it should be built, the design codes, how it should operate, what safety systems it should have, what sort of radioactive dose limits it should operate to for the workers and for the public. The Office for Nuclear Regulation in the UK has done that for this particular design, and it spent a long time doing that. So EDF Energy spent years going through the design of this before it was approved by the Office for Nuclear Regulation. So you may think that's an absolute fantastic development, from the Hanford B or Chicago Pile to Hinkley Point C, one of the most expensive and largest buildings in the world, and probably one of the most complex as well in terms of what it's doing, in the space of 75 years. But it's, well, let's have a look at that. There's a Model T Ford. It's a car that was built in the 1910s, early part of the 20th century, and that other car there, that's a Model S Tesla, if you don't recognise the shape. So there's 100 years of development in the motor world. We've got something that's pretty primitive into the way, you know, it's got all the basic features, it's got an engine, it's got the steering wheel, everything like that, but it doesn't bear any resemblance at all in the type of machine we've got there, essentially one that can drive itself to a certain extent. And that's what we're seeing in terms of the development, and also the future reactors that we're thinking about now. We're looking at the equivalent step from a Hanford B Chicago Pile equivalent of a Model T4 to a Hinkley Point C, or even a small modular or fast reactor of the future. The development we've just seen from Hanford B into Hinkley Point C has always been under the shadow of proliferation, and this has always been one of the difficult political strands to deal with in the civil nuclear industry, to distinguish ourselves and make a clean break and show that we're not part of the military anymore, because we share the same origins. The original reactor designs were there as plutonium factories. They were there for military purposes, and there's still that aspects of, well, nuclear power is still linked in some people's minds with military power, and that word proliferation crops up many times with respect to different aspects of the nuclear fuel cycle, because it's all about the spread of materials and know-how into military areas. Now, the original weapon states, US, what was the USSR but is now Russia, UK, France and China, we all had our own independent weapons programs in the 1950s, and we developed our own weapon systems, and we became the permanent members of the UN Security Council in doing that, and is referred to as a club. But there was a realization amongst these countries, amongst ourselves, that if everybody had these weapons, the world would be an absolutely horrendously dangerous place. It was dangerous enough as it was between the US and the USSR and ourselves in terms of a Cold War, and therefore there was these test ban treaties that started to be created and were signed up in terms of the 1960s and 1950s, whereby new weapons would not be tested in the atmosphere, would not be tested in underground situations by the weapon states that already had them. Of course, there are new ways of, different ways of testing whether or not a weapon or a weapon system is credible and it will work, but by doing that, first off, there was a signal that things like the environment were going to be taken into account, because we've all seen videos of nuclear weapons being set off on coral islands or nuclear weapons being set off in the Nevada desert, and that did create lots of radioactive particles that went up into the atmosphere. So there was an effect outside of the main areas, and of course there's a political effect to say that if we as a country say that we will not do this type of activity in the future, it sends a signal to people who perhaps trying it for the first time that you shouldn't be doing this neither. So it's leadership in that regard. And it also sets us on the path of looking at proliferation politically to say, how could we control that and make sure that proliferation doesn't occur? And the impact of that leads to regulation of the civil nuclear industry. So the civil nuclear industry operates under very strict international regulations and guidelines, which was born out of this need to control and maintain and reduce and hopefully stop proliferation of this nuclear weapons technology. Hot on the heels of the Manhattan Project and the Hanford B reactors, the UK developed its own weapons programme in the late 1940s, and it constructed these two large reactors at the newly formed Windscale site, which is now Sellafield, and they were referred to as Piles 1 and 2, and they were based on a graphite core, so similar to the Chicago Pile as well. They were air cooled, so air was dragged through the core and up these cooling stacks here that were large concrete chimneys, and at the top of the chimneys were these large filter housings which were able to take out any dust or particulates. At the time, the lead engineer, Cockcroft, insisted on these filters being put at the top of there, even though they were not seen as necessary at the time. That's why they're referred to as Cockcroft's folly. Now, in fact, that proved to be extremely beneficial because there was a fire in Windscale Pile number 1 in 1957, and the graphite core essentially started to burn, and some of the fuel cans were ruptured, releasing quite a lot of radiation and radioactive particles into the air, most of which, and the vast majority of which, were captured by that large particulate filter at the top. And if it hadn't have been there, it would have been far worse in terms of the contamination spread. Interesting on this particular photo, it's taken after 1915, probably late 1950s, because you just see in the background there, and those cooling towers as well, the actual civil nuclear program, and those are the Caldor reactors, which I'll refer to in a couple of slides. So I've been talking quite a lot about the military programs and how the first reactors in the US and the UK as well were there to provide material and produce material for the military programs that the two countries had, and also overseas as well. In fact, whilst the material production reactors were being built and operated, thinking about power production and thinking about nuclear power as a power technology was going ahead as well. And in fact, the first reactor to be used as a means of generating electricity or generating power was actually nuclear propulsion on a submarine, and the US launched USS Nautilus in 1954 using modularization of reactor technology, and in fact it was a water-cooled, effectively the first water-cooled pressurized water reactor, was modularized, reduced in size and installed on the USS Nautilus. So the type of reactor technology that went on to dominate the world as we see today was first launched on a submarine. That's where we leave the first part of this lecture. We've now reached a stage in the 1950s chronologically where we developed an understanding of nuclear physics, we've developed an understanding of nuclear fission, and that's led us to the creation of the first fission reactors, primarily aimed at material production to support military programs. But as you can see, we've launched and created the first power reactor, a water-cooled pressurized water reactor that's producing electricity for military purposes, but that shows we can use the technology and go on to generate power. And in the next part of the lecture we'll see how the technology is transferred into the civilian industry and how nuclear power rises as an important means of generating power throughout many countries.